First presentation is given by Dr. P.D. Krishnani, BARC. He's a head reactor physics division, design division. He's an expert of reactor physics, design of experimental and power reactors, neutron transport theory method, and fuel cycle analysis. His presentation topic is physics considerations for utilization of thorium in power reactors.
Thank you, Chairman, for your kind introduction. Good evening to all of you. This is the penultimate talk of penultimate day. I will be giving the work being done in RPDD regarding the development of advanced heavy water reactor and some flashes of MSBR. So the outline of my talk is, first I will just give some advantages which have not been spoken in this conference. Then experience with thorium fuel cycle. This has been dealt by Dr. Vijayan in length, so I may skip this. And then studies for large scale utilization of thorium fuel cycle in HWR, followed by Indian MSBR. So as you know, one of the important thing is the sigma fission to sigma capture cross section of uranium-233 in the thermal energy range highest for uranium-233 compared to others. That means more and more multiple recycling can be done with uranium-233. This is one of the important aspects for the development of this fuel cycle. Another aspect is the capture cross section of thorium is roughly 2.5 times that of uranium-238. That means in order to compensate the higher absorption in thorium, the enrichment has to be much more. Further, if you want to really take advantage of thorium cycle, the burn-up also has to be large. That means this further calls for higher enrichment. That means the total absorption cross-section of the thorium fuel is much more. Because of this, it offers very good competition to other structural materials. You can afford to use, say, light water as a coolant. So that is another aspect, and that is why in HWR, a light water coolant has been considered. Another advantage of thorium is, this is of course known, that it offers a very good material for the disposal of the plutonium. It is as good as inert matrix, but the advantage, one of the advantages is this, that the reactivity coefficients are negative with this compared to inert matrix. So this material is better than inert matrix. If you are using thorium in once-through mode, because uranium-233 production, you have to use higher amount of fissile material. So in order to get the maximum benefit, you ought to have higher burn-up, and fortunately it is seen that, this is an example in typical PHWR, where for the low burn-up, discharge burn-up, it is the uranium cycle, normal uranium cycle is better, whereas at higher burn-up, say more than 40,000 or 45,000 megawatt day per ton, thorium offers advantage. So you have to use it higher burn-up if you want to use thorium. And anyway, this is known that there are certain elements which give hard gamma rays. This can give rise to high proliferation resistance of this fuel cycle. And this has been told that the thorium has been used in number of research reactors, followed by Purnima 2, where certain experiments were performed with uranyl nitrate solution, followed by Purnima 3, where the experiments were done with uranium aluminum dispersion pool prior to using this fuel in Kamini reactor, which is a Kalpakamini reactor. This is the only reactor operating in the world with uranium-233 fuel reactor. Then certain irradiation has been done in Cyrus, particularly pure thorium rods, and as well as thorium-plutonium MOX fuel. Then some irradiation has been performed in Dhruva reactor, and finally in FBTR, as you heard today morning, and lot of irradiations are being done in FBTR. And as far as thorium utilization is in a power reactor is concerned, the first time thorium was used in a unique manner, because when you are starting the PSWR core, the power distribution is very peaked one, and whereas equilibrium power distribution is flat, relatively flat. If you want to obtain higher power from the beginning, you have to achieve some power flattening. This can be done by using either, say, depleted uranium or thorium. We are the first country to use thorium for this purpose, and by using only 35 fuel assemblies of thorium, a very good power distribution has been obtained, and it was possible to obtain almost more than 95% of the power from the very beginning itself. Now, then apart from this, lot of studies have been conducted to use thorium fuel cycle. For example, studies have been conducted to use this thorium fuel cycle in PSWR, BWR, and PWR. And the fuel consisted of thorium LEU, then plutonium thorium mixed oxide. This plutonium of reactor grade as well as weapons grade was considered for this purpose. And so this was the aim, was the plutonium disposition was this aim, whereas the aim of the thorium LEU fuel cycle was basically proliferation resistance. That was the main aim. Other studies have been conducted. For example, self-sustaining equilibrium thorium cycle in PSWRs have been studied. Then once through thorium cycle has been studied. Other use of this thorium-plutonium MOX cycles in PSWR have been studied using 2.4% plutonium as well as 2% plutonium. These are the certain studies which have been done for existing reactors. Now I will come to the main talk of today's main talk, which is nothing but the advanced heavy water reactor. The main aim of the advanced heavy water reactor is to test all the thorium technologies on the industrial scale. Plus, we had to also make see the other safety systems which will be used in the third and fourth generation of reactors. This is the main objective, and the advanced heavy water reactor is a 300 megawatt electric vertical reactor having pressure tube type. Coolant is boiling like water reactor. Moderator is heavy water reactor. If you will observe that it marries all the good properties of PSWR as well as BWR. So it marries both the better qualities of light water as well as heavy water reactors. And the main features are, it uses the natural circulation for the coolant. It has negative void coefficient in all the burn-up range, and lifetime is 100 years design life, plus there is a online refueling in this. Actually, two fuel cycles are being considered. One is thorium uranium-233 PU MOX fuel in closed cycle mode. This will be termed as ASWR reference core, and in another mode where thorium LEU MOX fuel will be used, and LEU will consist of 19.758% uranium-233. This is in the once-through mode. These are the two modes which are cycles which are being considered, and this advanced heavy water reactor has many passive features like core cooling by natural circulation, negative void coefficient of reactivity, large heat sink as gravity-driven water pool, passive core decay for heat removal, passive containment cooling, emergency core cooling injection in the fuel, core submergence, double containment. Plus one more feature it has, that is passive poison injection in the moderator. This can be used in the event of non-availability of the both primary as well as secondary shutdown system, or due to malevolent insider threat. To tackle both the things, this passive system can be used. Now, I will describe one by one both ASWR reference core as well as ASWR LEU core. Actually, for starting any PSWR, initial core has to be slightly different, because otherwise if we use the equilibrium fuel cycle, equilibrium fuel from the very beginning, the core is so reactive, you may have to use lot of poison and it may lead to positive coolant temperature coefficient, etc. To tackle this problem, core has to be slightly less, slightly less reactive. So initial core has to be different from the equilibrium core. So for example, in ASWR reference core, initial fuel consists of DU-PU MOX fuel. To start with this fuel, we can go, there's a transition fuel, because if there is no, the equilibrium core uses thorium, plutonium, uranium-233 MOX fuel. And suppose if uranium-233 is not available, we have to generate in situ this uranium-233. So there is a transition fuel cluster, THPU MOX. This will be used for transition purpose, and we will get uranium-233 from this, which will be subsequently used in the equilibrium core cluster after a couple of years. This transition may take 15 years or so. And in case if the uranium-233 is available in the very beginning, then this transition period can be 0 year. That is, we can, if uranium-233, sufficient amount of uranium-233 is available in the beginning, we can directly come from initial core to the equilibrium core, or it may take at the most, say, 15 years of time. Also. Fuel, whereas in fuel cycle in the ASWR LEUs, initial core consists of thorium, 13% LEU MOX, and finally we recycle with equilibrium fuel cluster, and directly it comes to equilibrium fuel cluster after some time. So what is the fuel of these two? So I will, as I told you, initial fuel cluster may be slightly different. I will not describe much about that. I will directly describe the characteristic of equilibrium core, because that is what will determine this. So even though we have studied all from transition from initial core to the equilibrium core, etc. However, for this purpose, today's, I will be only giving the equilibrium core characteristic. So ASWR reference core, in both the, as well as ASWR LEU core, they use 54 rod cluster. In the reference core, first two rings have thorium, plutonium MOX, whereas in the third row, the outermost ring uses thorium, uranium-233 MOX. And in the last pin, the fuel is graded along the axially, and there is the outermost ring, for example, contains 3.3% uranium in the upper half, whereas 3.8% uranium in the lower half, to achieve the bottom peaking, which is better from thermal hydraulic considerations. In ASWR LEU core, it is only thorium LEU fuel. So for example, first two rings have 30% and 24% LEU in thorium, whereas in the outermost It is actually graded. The upper half has 14% and lower half has 18% LEU in thorium. So basically, as far as reactor, both the reactors are same. Power is 300 megawatt electric. Main difference is thorium uranium MOX plus thorium plutonium MOX fuel in HWR reference code, whereas here thorium LEU fuel. According to this, the discharge burn up in this is 40 gigawatt day per ton and 60 gigawatt day per ton for the thorium LEU. Other small difference between these two reactors is there are number of fuel channels in this 452. Here 8 channels have been reduced because there was more need for the shut-off rods. So accordingly, there are 37 shut-off rods and 45 shut-off rods in this. So in these are the major differences between these two designs. Otherwise, they are of similar type. So basically, if we see, most important thing about this is the differences between main is the reactivity coefficients. If you see the reactivity coefficients in the HWR reference code, the channel temperature coefficient as well as moderator temperature coefficient, they are positive. And this can be handled very easily because the total change in temperature for this is very small and it introduces hardly very small reactivity, and this is being handled very efficiently in the present PHWR. However, in HWR LEU case, all the reactivity coefficients are negative. So this is, in this respect, HWR LEU scores higher. This gives how much power is generated from the thorium uranium 233. So if from this it can be seen that power fraction coming from the thorium uranium 233 is 60% in the case of HWR reference code, whereas 38% it comes from the thorium LEU core, HWR LEU core. So this is the only reactor design where such a high power fraction comes from the thorium uranium. None of the other designs in the world uses this much power from the thorium uranium 233. This gives the actually uranium as well as plutonium isotopic vector for the discharge burn up, and it can be seen from this that the uranium coming out of this discharge from the reactor has very high percentage of uranium 232, maybe 2500 ppm of uranium 232. And another thing it can be seen is there is a very small percentage of fissile component of plutonium 239 as well as plutonium 241. So there is hardly 35, it contains hardly 35% of fissile PU. Thus, this reactor really acts as a very good burner of the plutonium. Starting is 75%, whereas when it is discharged, it has only 35% of the fissile PU. If we see the similar characteristics for the HWR LEUC, of course here it has uranium 232 as 200 ppm or so, but it has very high percentage of plutonium 238 and it is as high as 8.6%. So this really acts as a highly proliferation resistant fuel as far as this core is concerned. So whereas another thing is the discharge uranium contains about 8.2% of the fissile, 5.83 uranium 233 plus about 2.38% uranium 230. So this fuel, if a decision is taken, this fuel can be reused in other reactors if a decision is taken. So overall, the plutonium discharge has very poor quality, 57.5% plutonium, but because a core contains only 20% uranium 238, hardly, so plutonium production is very, very small. So as far as proliferation resistant characteristic of this core are concerned, they are very superior, and this is being proposed in the export model that this fuel should be used. Actually, former chairman Anil Kakotkar on his first day actually proposed a reactor for PHWR also on the similar lines. Let us see the fuel economics actually. In the AHWR reference core, annual requirement of uranium is 90 kg, and it is self-sustaining. Actually, it comes from a reactor itself gives more than what comes out. Uranium comes out is 110 kg, so it can be comfortably made. And whereas the annual requirement of say plutonium is 150 kg. So even if we do not consider whatever plutonium is coming out, so if you see that actually 1 megawatt electric of PHWR, whatever a plutonium it gives, same plutonium can be used for the AHWR LEU core. That means if you see the fuel utilization point of view, 1 ton of natural uranium, whatever plutonium it gives in the PHWR, same plutonium can be used to run this AHWR LEU core only. And whereas for AHWR LEU core, annual requirement of LEU is 760 kg. And another good point about this course, minor actinide discharge annually in AHWR LEU core is very, very small, only 2.4 kg. And let us see to the natural uranium resource utilization. This is the point where you have to concentrate. The natural uranium, that is in ton per terawatt hour production, it is 21.7 for the KK project, that is PWR type of reactor, and in PHWR it is 20.2 ton, whereas for AHWR LEU core it is 19.48 tons per terawatt hour. So as far as fuel utilization characteristics are concerned, they are quite superior for AHWR LEU core. So just summarizing, the AHWR reference design is very good, the fuel requirement is less, and power from thorium is very large. In nutshell we can say. And for the AHWR LEU design, as LEU has been found to be very good external feed for thorium oxide. LEU content is only 21.7%. This is equivalent to say 4% of uranium-235, 4.2% or so. And this gives 60,000 gigawatt day per ton of burner. Fissile uranium requirement per unit energy is significantly lower. About 38% of power comes from uranium-233, thorium. The uranium in the discharge fuel has 8.4 fissile content, which can be used in other reactors. The discharged uranium is denatured and contains significant amount of uranium-232, so it cannot be used easily. It can, as far as proliferation resistant characteristics are good, they are very good. Further, it is the discharged plutonium has only 57% fissile, and that too it contains 8.5% of plutonium-238. Plutonium produced per energy is much less in the case of AHWR LEU, because 80% contains thorium. The presence of uranium-232 in the processed uranium and plutonium-238 in reprocessed plutonium enhances its proliferation resistance characteristic. Minor actinide production per unit energy in this reactor is also very less. So this is what I wanted to talk about AHWR. Now I will give briefly, very brief, in 5 minutes or so, molten salt breeder reactor, which is that at present we have just started working on this system. So very preliminary things are there. Actually, quickly if we see, one of the important things about molten salt reactor is online refueling and reprocessing is possible. It offers better neutron economy because of these features, and fuel drained to critically safe storage tank during oxygen. These are the important features which are further drivers, apart from many other advantages which it offers. If we see presently the reactors which are being considered, thermal, epithermal and fast systems are being considered for uranium-233. in all respect, breeding ratio, monitor lifetime, feedback coefficient, from all these consideration, the fast reactor scores higher. Only difficulty with the fast system is it requires fissile inventory per gigawatt electric may be very high. It may be of the order of 5 ton, or at least this order. So this is the only negative point about the fast reactor. Otherwise, in all other respects, this is superior to the thermal spectrum or epithermal spectrum. So looking at this, and these are the certain MSR concepts being followed in the worldwide. Only I think I want to say that wherever thermal system is there, the breeding ratio is varying, is around 1, but it varies from say 0.95 to 1.97 of this order. So it is slightly, it is a more acting as a converter rather than breeder. Whereas if you want to use it as a breeder, it has to be used in the fast spectrum, where it can be of the order of 1.12 or so. So looking at this, we started working on the fast MSBR concept, and we are right now considering both loop type option as well as pool type option. And before proceeding for this, because fast normally our codes are tuned with thermal range, so we wanted to first check our modeling and other things for this system. So first thing we did, we analyzed the MSFR, molten salt fast reactor, French reactor first. So when we analyzed this, actually we obtained breeding ratio of the order of 1.17, initial fissile inventory 3.2 ton per gigawatt electric, and the spectrum which was obtained is very similar to the one given by them. So as far as, so this establishes that the calculating power which is there can be easily used for this type of system. And then a number of MSR concepts, for example, loop time design, number of things. The fuel which is being considered for this is lithium fluoride, thorium fluoride, and uranium fluoride, with different uranium fluoride concentration changing from say 2.5% to 3%. It has been seen that 2.7% may give the required things, and where the total conversion ratio, initial rather, what we are talking is not cycle, but only initial conversion ratio is of the order of breeding ratio is of the order of 1.09. So this is one option which is under consideration right now. Another pool type, basically it is same, only difference is because whole reactor is submerged in the pool. So initial fissile inventory is very high, otherwise same 2.7% of uranium fluoride will be enough, and it gives breeding ratio of the order of 1.1. So both the things are under consideration. Some studies have been performed. If we want to recycle the fuel, how the reactivity will change, all these things, because we are trying to, yes, fuel is circulating, so we have to change and how to calculate all these things. This is being actually, this is one example where we can do all these things also, recycling as well as refueling. Both the things are being simultaneously considered. Then safety studies, if we had to do for the recirculating fuel, because fuel goes outside, some of the delayed neutron comes out. Because of this, effective delayed neutron fraction in the core is smaller, and depending upon the speed of the flow, the delayed neutron fraction can be as low as 300 ppm compared to 700 ppm. So that is hardly 3 milli-K compared to 7 milli-K. So we are actually sharpening all the tools required for this, and it has been seen that compared to other calculation, our calculations are matching with this. Then, of course, another program, safety study, continuing the safety study, we are trying to develop point kinetic code for the delayed differential equation solver. We are trying to solve this for the circulating type of the reactor. And preliminary results which we have got are very encouraging for this. Then finally, actually, we are trying to design a 5 megawatt thermal experimental MSR facility. Right now, we are working on this. The initial thing, only I want to say that about fissile inventory for this 5 megawatt thermal reactor will be of the order of 30 kg or so. And this may be, and total requirement may come out to be 50 kg if we want to refueling, if we take into account refueling for a couple of years. Overall, summarizing the things, simulation methodology has been examined by simulating MSFR for reproducing key results. Two types of core configurations are being considered, loop type as well as spool type. Fast spectrum offers greater design flexibility and higher building ratio. MSR long-term alternative to solid fuel reactor with several advantages and unique potential. For example, inherently safe, breeder, high burn-up, and better fuel utilization it gives. With this, I thank you for your kind attention.
Thank you very much, Dr. Krishnani. So the paper is open for the floor. Do you have any questions and comment? Yes.
Thanks for the nice presentation. Yeah, I think the power from thorium is actually the power coming from the U-233 that you have fed into the thorium.
Yes.
So it's difficult to say that it is directly power from converted uranium, etc.
Yes.
Every time you have to feed. Other comment I have is once you say that I'll be doing self-sustaining, I think the uranium vector is continuously changing in each cycle. I think you will have more proportion of 34, 35 and other things.
It is like this.
In a multi-cycle, maybe it has to be
No, we had done the multi-cycling also. In one cycle, for example, from 80% we are starting, it is 75%. However, the requirement is 90, and we are generating 80 kg or so. We are generating, say, 100 kg. So there is enough scope to consider all these things, and we have considered the multiple cycling actually. So up to 5 cycles we have done this analysis, and it has been found to be, we can tackle these things.
And the plutonium you said you will be met from which source?
Plutonium will come from the PSWRs actually.
Okay.
And regarding first comment, it is correct, but in LAU, it is precisely from uranium-233 which is generated. Whereas in the reference code, yes, whatever you say is correct.
Okay.
Okay. Is there any other? Yes, please.
Sir, I just have only one question. That how do you take care of the mixing? Suppose in one cycle there will be some fission products which are formed.
Yes.
Whenever it is going to the core, then there will be some mixing taking place.
You are talking about MSBR?
Yes, MSBR. So how do you take care of those in the calculations of?
Actually, this is what we are developing actually.
Then you have to consider the hydrodynamics.
Right now what we have considered is fresh fuel which is being coming, but we are now actually considering these things also. Whatever you are telling, different type of fission products can be kept there, and we are able to simulate.
K effective will change. What
yes, they will change.
It will change.
Yes.
Dr. Krishnani, you
Yes.
have done much of the calculation presentation only on the reactor physics part.
Yes. Because
When you
other things were covered by.
When you combined reactor physics with thermohydraulics,
Yes.
particularly when you have got 440 channels plus,
Yes.
and all channels are boiling,
Yes.
if they can be flow distribution oscillations,
Actually, we had
what
done.
is the impact of that on the reactor physics and other things?
Actually, from there only, it has been decided that we have to obtain the bottom peak power distribution. Because of that, lower half in the last ring actually has higher enrichment compared to the upper half. Because we want to get the bottom peaks. It comes from the thermodynamic considerations only actually. So we had done these iterations also. Thermodynamic physics iterations have been
steady
done.
state.
Of course, I have not presented here. That I agree.
No, that is for steady state. If there is oscillations or instability,
Those things are also being done actually. Because I wanted to give crisp features which are good for the PSWR, which can be
Yeah, I appreciate that.
Yes.
Thank you.
Different.
Thank you very much. So time is running out. So thank you very much, Dr. Krishnani. Let me give him a small gift on behalf of organizer.